this. I guess we'll do this way. So part of, this is kind of, it's named basic measurements, but it has a lot of things. What we're doing in here are different sensors. So pretty much, I guess, all of the measurements that we'll make other than calibration type measurements are some type of electronic sensor. So we started with the thermistor. I think we do maybe the photoresistor next, and we do Hall effect sensor. And so all these digital type sensors or analog sensors. And part of what the job of measuring, whether you're measuring for some kind of experimental type thing, or these are attached to some in-service machine and you're getting performance data, you always have some amount of uncertainty associated with the measurement that you're making. Is your calibration perfect? Is there some just built-in error in the thing you're using to measure or in the process you're measuring? And to deal with those, you can't always, and actually you can never get 100%, unless it's like on and off type situations. You can't get 100% accuracy. So you have to deal with these probability and statistics behind the scenes on your measurement that you're making. So how certain are you that what you actually measured is the true measurement? And so that goes back to these statistics. So we're just going to talk about some of them today, and some of the base background stuff. So some of this stuff should be things that you've seen here and there scattered in the math series. Maybe if you've taken a stat class, Stat 405 is a decent one to take you can even count as your one of your elective classes. So it would be a useful class later on, particularly if you enjoy that kind of stuff. So we're going to look at a couple of, just so we all agree on these definitions. And just we're going to call statistics the study of the collection, organization, analysis, and interpretation of data. So you got a pretty broad thing. Basically, it really kind of boils down to these analysis and interpretation. What does it actually mean when you took this measurement? Does it mean you need to change something in your machine, or what are you doing? How do you interpret the results of this number that you might get out of a sensor? Let's go ahead and get two of these. All right, so population and sample. These are terms within statistics that talk about the number of things you're measuring. So the population is if you're able to measure everything out there. So you measure all of the possible pieces of whatever it is, all the humans in the world. You took the entire population measurement for their height. Normally you can't do that. Normally you don't have access to the entire population of whatever it is you're trying to measure. So instead, or it's too cumbersome to do it. Even if you have all of the things, it's too cumbersome to try and measure all of them. So what you normally do is you take some random sample. So you take a little subset, and that's the thing. You measure all of them. And the sample is, that's more like what we're going to do most of our time. But we do need to make a distinction between if we're measuring a population or if we're measuring a sample, because the equations that are associated with them are slightly different. And the variables names are different, and the symbols you use for the mean and standard deviation look different. Random variable, so this is the thing that you're measuring. Discrete and continuous, so discrete has states that it can be in, so a finite number of states. So they give the example here of tossing a die. So if it's got 6 sides on it, it can be 6 things. I guess it's possible that it rolls in a way where it lands on an edge up against something and it doesn't, resolve to one state or another. But in general, discrete means there's a finite set of outcomes, where continuous is there's actually an infinite amount of outcomes depending on how many decimal places you want to throw behind the measurement. And most of the things that we end up dealing with, the analog ones, so the temperature, temperature has this gradation from some low end to some high end, and in between there, it could technically be any little value. You just put in more decimals behind whatever it is you're reading, and it's a slightly different number. There's infinitely many options between any 2 points. So it's called continuous, and so those are the analog readings, and discrete are more like the digital options here, where there are set options for it to either be a 1, a 2, a 3, whatever it is. And so we do need to know the difference in those two things. Distribution function. So we have to decide on this. Let's go back on the statistics side of things. We have to decide how, if we took a whole bunch of samples of this thing, how does the distribution look of if we were to plot a histogram or a frequency plot of all of the things that we recorded? What shape does that have? So is it, and these are some of the terms here. So symmetric, is it basically equally distributed about some average value or mean value? Or is it skewed? So is that little, if you're thinking of the something like, let's go over here. We don't need those yet. So let's move him down. All right, so you think probably you've seen that kind of shape. So that's symmetric. And it looks like, if there's some average value in the middle. So this would be a continuous representation. If you were showing this as like a histogram, you'd have something where, there's these little bars that more or less map to this same shape if it was a histogram. And so this one is symmetric. There's a middle mean point, central tendency, and everything's evenly distributed on either side. I think the next one that was in the list was skewed, so it's that hump. There's a tail on one side compared to the other, so it's not even symmetry about the mean or the central tendency. J-shaped, so it looks kind of like the Nike swoosh sort of. Bimodal, there's two of those averages. So these would be, the J-shape would have some, basically kind of the upside down version of that. Bimodal shows up when there's two contributing factors to whatever you're measuring. So if you took average height of a population of humans, in general, you'd have a bimodal distribution between males and females. They'd have a slightly different average, and it shows up in the data. What was the other one here? Uniform. Oh, so like on the dice rolling, you would think a normal dice, if it's six-sided, you have an equal chance of getting a 1 or any number through 6. And so you should have a uniform distribution. You shouldn't have the dice or the die rolling one number any more than any of the others, unless there's something weighted about the actual die itself. So those are good things. In fact, this is generally, when you're taking this kind of data, a large sample or a population, one of the first things you want to do is plot some kind of histogram or frequency bar chart to see what kind of thing are you looking at. Does it even look like any of these? Because some of the stuff we'll do later depends on the data looking like one of these options. In fact, we're usually going to assume that's going to look like the symmetric one, the bell-shaped one. If it doesn't look like that, then some of the things you want to do statistically won't apply, because you're assuming that it's symmetric. And most random data should be symmetric, unless there are things that skew it, towards one end or the other, or maybe a bimodal thing where there really are two dominant factors that are controlling the data. But if it's either of those things, then, or uniform even, that would obviously not work with some of these equations. So we kind of need them to be this symmetric looking function. And then the probability is, a lot of times you hear probability and statistics together. The probability is just what's the chance of something happening. So if I'm rolling a six-sided die, I should have a 1 in 6 probability that any given number is going to be the one rolled. Histograms, we kind of talked about that. That's basically drawing one of these bar charts of frequency. There are a couple of rules, or not rules, guidelines. There's a couple of guidelines for how to make good histograms. So the first thing you kind of want to know is, do you even have enough data points that you've collected to generate a histogram? If you've only collected like 5 data points, you can't really make a histogram. In general, a good cutoff point is 40 or maybe 30 would generate an okay histogram, but about 40 points, 40 samples is about the minimum you want to generate any kind of meaningful histogram. So once you've got the data points that you've collected, then you want to determine the range. So that's just the largest value subtract the smallest value. So what's the range of the data that you're collecting, so that you know basically the endpoints of a histogram. Then you want to divide the range by the number of bins. The bins are the bars themselves in the little chart. You kind of think of them as bins, like buckets that you sort all the different data into. All the buckets or the bins have to be the same size, because if you have one big bucket and a bunch of little buckets, then more things are going to go into that that bigger bucket. And what you're trying to do is basically the width of all of these buckets or bins. If it's not the same, then that will obviously change what the histogram looks like, because what you're plotting here, this height, and this is why it's also called a frequency plot, is how many things are in that bucket. And so this number here is going to be like 10, and then this one's 8 and 6 and whatever they end up being. But the heights of these bars are how many things fit into any one of these bins. And if you have different size bins, then obviously a bigger one is going to hold or contain more of the items that you're counting. Here's kind of a number of data points and number of bins. There's a general rule that the number of bins is more or less the square root of the number of data points. So if you have 50 data points, the square root of that's a little over 7, so you have about 7 number of bins. And the same thing here is showing that you should have 5 to 7 bins. It's not like mandatory that that's what you follow, but in general, if you take the square root of your sample size, that is roughly the number of bins that would work well with that sample size. This one's just breaking it out more as just some different ranges, but in general, like the square root of 100 is 10, so kind of works. There's another histogram plot or a frequency plot. So that's one of the first things you want to do when you collect data that you think is random, is plot it in something like a histogram or frequency plot to see if it really does look symmetric or any of these others, bimodal, if it's skewed one way or the other, because the things you're going to do mathematically later depend on what shape this plot looks like. So determine the bin width, so how wide, like they call it H right here in the plot. A convenient formula is basically the range R, so the smallest number to the largest number, what's the difference in those two, divided by K, which I think K is the number of bins is what they have. So basically you just want all the bins to be the same width. And you do want to, I was going to say, you do want to round the value off so that you have a reasonable bin width. You don't really want them to be these hard to follow bin widths. So like you wouldn't want a bin width necessarily that's 7.459 units wide, because that's just kind of hard to deal with. Make it 7.5 or even 8 if it's depending on what you're measuring. So you normally want these bin widths to be relatively rounded off. You don't have to chop off all the decimals, but you don't want a whole string of decimals on this either. You got to choose some starting point. So normally you have a couple of empty spots on either end of your histogram. You don't normally jam it up against the y-axis. And then you go through the list of items in your data set and sort them into these different size bins. And plotting the number of items in each bin generates the histogram. Now there are, like Excel, you can go in and manually do it, create a bar chart with the different heights of the bars being the frequency of samples in each one of the bins. But Excel also has just a histogram it's not a, I guess it's we'd call it a function. It's an add-in for Excel. And it will take your data, you generate the bins that you want it to fall into, and it just goes through, sorts it, and creates the histogram and everything for you. So it doesn't matter how you do it, it's just you want to generate one of these histograms. So here's example one. So this goes back to the exam grade. So we need to get that file, and then we're going to create, this is going to be in Python, by the way, so we're going to do this in Python. So if we go get, let's see, actually, it's going to look like that, I suppose. But let's go do it. Let's see. Nope, don't save that. So example one is the code, and then we need this data set for it to read. So let's save this. I don't know where it saved it, so let's put it on the desktop so that we know where it's at. And we're going to go into our 380 or my 382 folder. I've got a folder in here where I've put everything. I don't know if I've already put it in here or not. Let's see, where did it save it? Well, I thought I put it on here. I'm pretty sure I did. What was it named? ENGR. Why am I not seeing it? Don't know. We'll do it this way. It went somewhere. I don't know where. All right, so I'm putting it in the little folder I've been using here. Don't know where it went the first time. And then we'll get this example one. It's already written for us, so we'll go through. What's happening in this file. I'm loading up our Python edit. There it goes. All right, get a new one. Paste that in there. Copy. All right. So let's see. First of all, so this file name here is the file that we're trying to read from. Now it has put it in or it's assuming that the file name that I just downloaded and put into a folder is in a subfolder called data. I'm just going to erase that because I didn't put it in there. I put this file name in the same folder. Actually, I haven't saved this yet, so let's save it, and then they'll be together, and they'll work, hopefully. So there they are. Oh, this is called, we just call it example one, and it's about statistics. All right. So now the Python code and the little file that it's referencing, exam grades, engineer 120 exam grades, TSV, they're in the same folder. If you don't change that path, then you need to put ENGR 120 exam grades in a folder called data that's inside the same folder where you save the Python code. I just didn't want to do that. All right, so we need a PyPlot library so that we can do some plotting because that's what it wants us to do. Here is, we're going to open the file called file name. It goes up, it references, oh, file name is that thing. So it goes and finds that file and opens it, and it reads it in, and it strips off any empty spaces. You could print it here. If you uncomment this print line, then it'll print just so you can confirm that it actually read in all the data the way you intended for it. Those are good things. Whenever you calculate a variable or you read a file or whatever, it's good when you're developing this code. Now, we just downloaded it. I assume it works. We'll have to run it and see. But it's good to have these little debugging print statements after an action so that you actually can tell that it's doing what you intended for it to do. And then you comment them out later. You leave them in there. There's no reason to like erase it. Just comment them out and so that they don't execute every time, unless you want them to. Here we're converting the file into a list. Let's look at the file itself and see what it looks like. So I should be able to just open it with something like Notepad. We'll open it with Notepad++. Okay, so it's just a title at the top that says exam grades and then a whole list of numbers. A lot of numbers. Like 467. Well, it probably started at number 2. So 466 exam grades. And they're all over the place. So that's what we're expecting, but they're in a row by themselves. They're not separated by commas or whatever. They're separated by tabs, I guess. But it puts them on new lines. No, I don't want to do that. All right, so it splits them based on this /n is like hitting the enter key on your keyboard. So it's going to split the file based on wherever there's the end of line. Since ours was a single data entry in a row, basically. So you can split them based on other things like commas or tabs or whatever. This one did have that very first line said something about grades or exam grades. So we're going to pop that one off because we don't want that. We just want the numbers. Here, we are converting all of those numbers. So a thing that happens in most of these files when you read them in is they get read in by default as just a string or whatever. So we're going to basically populate. So right now we've read this thing into a file or a list of files called rows. And we're going to read it into an actual list and call that data. And we're going to, when we add a new number to this list, we're going to make it such that it's an integer so that we know that it's going to be an integer. A lot of times in Python, you can get away without typecasting your variables. In this case, we're just going to make sure that it's treating these as integers and not text numbers because we want to do math type things with them. So we need them to be integers. Here, this PLT, that's we imported the library PyPlot, MATLABplot from PyPlot. And so this is what we named it. So this is one of the plotting functions. So you're going to create a figure and create a 1 by 1. So it's just one figure. Remember, you can have multiple, like 2 by 2, and you have 4 different little graphs on the same figure. This len is a function for lists, and it says it basically determines the length of whatever is here, data. Data is the list containing all of the grades in it. So N, capital N here, will be the number of items in the list data. So the 466, and then, or whatever it ended up being. And then this prints it out. Again, this was one that's more for troubleshooting. You might comment it out later, but it prints it out so that it makes sure that we expect to have 466 items in the list. If we get some other number here, then something went wrong with us importing this data file. Here is we're telling it this is a new function that we haven't used anyway, saying that we, instead of a scatter plot, a line graph type thing, we want a histogram. So that's one of the built-in options in PyPlot is to use a histogram. You want to plot data. We have 460, yeah, there it is, 466 data points. If we took the square root of that, that's around 20. You know, it's a little more than 20, but 20 is good enough. So we say that we want 20 bins. And then it will do the rest. It'll figure out the range. It'll figure out how big each bin needs to be to have 20 of them. And it'll create the histogram. And then this is just labeling the graph itself so that you have axis titles and chart titles. And then the very last thing you want to do is actually show the plot. All of this stuff here just creates it. And then this one actually shows it, displays it on the screen. So let's see what happens. We run this. Oh, there it is right there. All right. So you should get more or less, and there's all kind of options to like outline these so that you can see the individual bars and all that kind of stuff. This one, you know, is it symmetric? It's not really. It's not really a perfectly symmetric distribution. So that would be good to know. You might think that exam grades are, you know, typically like a bell shape. But you know, they're not always like this, particularly in this particular class because it's the very first engineering exam, and so you do have got a little bit of a bimodal. There's a hump over here in the really low grades, and then there's kind of hump over here in the middle of this bigger group of people. And if you think about the people taking exam 1 in 120, yeah, this kind of makes sense. I mean, it's just, there's some people that just weren't ready for it, and then there's everybody else. And this one, you could probably get close to saying that this one is symmetric, although even it is skewed some. You know, it's skewed towards the lower end. There's a little bit of a tail going towards this end. Even when you throw this group out over here, there's a little tail going this way. All right, so that was really simple. I mean, technically, there's like 10 lines of code here and a whole bunch of comments. You get your data, you bring in a library to plot it, you open the data, split it up into rows, fill a list with all the data, and then the rest of it is creating the plot. You know, this line right here, line 42, is the whole thing that actually makes the histogram work in Python, assuming you're using the pyplot library. The rest of it over here is just setting up the data itself. Oh, I didn't look to see if it printed out. I guess that would have popped in the shell over here. Let's see. Oh, yeah. It printed out 466. So that is the print in right here, so that it was correct that it counted 466 items in the original data file, which is what we had expected it to do. So super simple to do. You can work around with the different ways to generate the plot itself, but not complicated. And that at that point, you can go in and decide, okay, now what kind of statistics can I do based on what this data looks like? Let's see, we'll close that guy, go back to PowerPoint. It's over here. All right. Oh, all right. So we ended up in ours, I think, looked exactly like that, which it should have. Okay. All right. So now we've got this idea of measure of central tendency. So all this is a really complicated looking equation. This is just calculating the average or the mean if we're talking about statistics. You're just adding up. So this X bar is going to be mean average value. And you're just adding up all of the items in a list, dividing by n. N's are normally going to be the number of items in a list, so the sample size. And then here's just the discrete version of this equation without having to spell out every little term in it. So you know what that is. So mean of a population is exactly that. Now you've got some different variables here, like you've got a capital N versus this lowercase n. You have mu instead of X bar, so there are distinctions on which one are you actually talking about based on, you can tell by the variables you're using. So lowercase n for sample size, capital N for population size, mu for population mean, X bar for sample mean. Median is you have arranged all the data in order and you pick the middle value. Or if it's an even number of data sets, then you can average or however you want to deal with it. Maybe they're both the same value in the middle, but there won't be one in the middle. You have to do something with the two in the middle. Mode is the one that occurs most often. And so hopefully you know all of these, or at least it doesn't take you long to remember them. Measure of dispersion. So this is basically how far does this data spread from this central tendency? So there's some center value, mean, that you can calculate, but you know that not every value lands on there. Not everybody made a 75 on exam 1. So there was some kind of spread between there. And so that's kind of where you start getting into the statistics of things. And we've got this idea of deviation just being a difference from the mean. So X bar, so this is a sample. So X bar is the sample mean, and X sub I is a single individual value in your sample set. So the I is just index, so it could be X0, X1, X2, X3, whatever, all the way to X sub n. and then DI is the deviation. So it's just the difference between any individual sample and the average. That's not particularly useful in itself because, I mean, it's kind of useful, but it's not normally used for anything other than, I don't know, you can calculate it, except it does go right here. It's the numerator, or part of the numerator, in this idea of standard deviation. So, and again, we're talking about standard deviation of a sample, not of a population right here. So I have this S, that's going to be standard deviation. And what you've got here is this numerator is the deviation, but some of these numbers are going to be larger than the mean. Some of the items in your sample are going to be smaller than the mean. So if you just kind of added them all together, like what we're doing here, we're kind of summing up. So you're summing up all these deviations. If you added them together, they'd kind of cancel each other out because you'd have a bunch of positive ones and a bunch of negative ones, a bunch that are bigger than the average and a bunch that are smaller than the average, and they kind of just wash out. So instead of that, you square this deviation so that now all the terms are positive, so that you can actually add them together and they don't cancel each other out. And then you divide by, instead of n, you do n minus 1, so that's the sample size minus 1. And since you squared it, you've enlarged it all, so then you take the square root. So this is a way to standardize this term deviation. So that's what standard deviation is. It's just a way to calculate how far off is the data on average, because you kind of have an average thing going on here. You've got a bunch of numbers divided by n minus 1 anyway. But you have made everything positive by squaring it, and then you undo the square by taking the square root, and you get this number that represents how spread out your data is. And there's a similar thing for standard deviation of a population. Notice you have mu and capital N in here and sigma as the variable. So the only difference here is that you're talking about you have taken every value of the population, and so you actually have a population standard deviation instead of a sample standard deviation. Most of the time in the real world, you're going to have sample standard deviations. And then variance is another term, that is just the square of one of these numbers, either the sample or population standard deviation squared. All right, so probability. This is the chance that some particular thing is going to happen, and it always ranges between 0 and 1. So 0 or 1 means that every time this thing is going to happen. So it's always going to be this. And 0 means it's never going to be this. Normally you don't have 1 and 0, you have some number between 1 and 0. So there's some chance or some probability that the thing is going to happen. And the closer it gets to 1, the more sure you are that it's going to happen. So here's some samples. So A and B are mutually exclusive, so they can't occur simultaneously. So you have a single die, and it can't be more than one number when you roll it. It can't be 1 and 3 at the same time. It can only be 1 or 3. So this is telling you the probability of rolling a single die, and it comes up a 1 or a 3. So A could be 1, B could be 3, would equal the probability of it being a 1. So there's a 1 in 6 chance that it's going to be a 1, plus the probability of it being a 3. So there's a 1 in 6 chance that it would turn up a 3. And you add those two probabilities together. So you got 1/6 plus 1/6. So you have 2/6, which is a third. So there's a 33% chance that you roll a 1 or a 3. That's if they're mutually exclusive. So they can't both happen. One of them prevents the other one from happening. If A and B, so it's a different one. So this is kind of the notation over here. A, B is they are independent of one another, but you want them both to occur. Here you wanted them either one to occur. So now they're independent of one another. So maybe now I'm rolling 2 dice. So the rolling of 1 die, or I'm rolling 1 twice maybe, or whatever, however you want to think of it. But I'm rolling 2 different dice, and I want a 1 and a 3. and I just want to figure out what are the chances of me rolling a 1 and a 3. So you multiply them you just multiply those two probabilities together. Now it gets tricky. So let's go over here. So that's why I had these things. So here I got 3 dice. So what if you wanted the result to be all ones? Is that different from rolling a 1, a 2, and a 3? Is that a different probability? I heard no, mostly. I heard maybe. And so this is a good example of almost always, if you're asking an engineering question, the first answer is it depends. So it does. This totally depends. And it depends on what I mean by 1, 2, and 3. Do I mean like the blue dice has to roll a 1, the red dice has to roll a 2, and the yellow dice has to roll a 3? Or do I mean I need any one of these to roll a 1, another one to roll a 2, and another one to roll a 3? Because those are different things. But when I say I want them to all roll 1s, then I've locked in, no, the red one needs to roll a 1, the yellow one needs to roll a 1, and the blue one needs to roll a 1. So I've told them exactly what they need to roll. So these are actually, it depends. They can be either the same probability or different, depending on what you mean by the second one. There's only one way that you can roll a 1, and a 1. They all have to roll 1. So they're determined already which one they have to roll. So the probability for this first one, these are mutually, they're independent. They're not exclusive. They're independent. So whatever the blue dice does not depend on what the yellow and red dice did. So it has a 1 in 6 chance of the blue rolling a 1. There's a 1 in 6 chance of the red rolling a 1. And there's a 1 in 6 chance of the yellow rolling a 1. And you multiply those together, so you get 1 over, what, 216? What is 6 times 3? Or 6 times 6 times 6, rather? 216, yep. Here we go. There's only 1 out of 216 possibilities to generate the first case. So 1 out of 216 chances. And the second case is either if it's this case, blue, red, yellow, then yes, that's the same probability. But if it's not that case, if I just want a 1, 2, and 3 combined in any set of the dice, then there's a 1 in 6 chance that the blue dice rolls a valid number. So let's just say that it's 1, 2, or 3. It could be one of those. But when it comes to the red die, or the next one, doesn't matter what order you go in, the next one, actually, there's not a 1 in 6, there's a 3 in 6, because it can roll a 1, 2, or 3. But the next one, the red dice, let's say that the blue one rolled a 1, doesn't matter which one it rolled, but it rolled one of the valid numbers. Now, the red dice has to be a 2 or a 3, so it only has 2 out of 6 chances of occurring. And then the yellow dice, maybe the red one rolled a 2 in that case, the yellow dice has to roll a 3, so there's a 1 in 6 chance. So this is different. I have a 3 6 times 2 6 times 1 6, so that's, I don't know, 1. Yeah, so 1/36. So there's a 1/36 chance of that event occurring. So you have to be very careful with this probability stuff, because just like most of the stuff out there, it depends on what you mean. If you mean a specific order, then okay, yeah, that's the same as 1, 1, and 1. Or do you mean just a combination of a 1 and a 2 and a 3 in there? Then that's a different thing, and you got a much better chance of that occurring. So you got to be careful with some of these statistic deals. The probability of the occurrence of A or B, or both. So this one looks weird because you think it's a typo, like there's a minus sign here, like, well, why wouldn't you just add both of these things occurring? So this is another one you got to think about. Let's think about this one with a deck of cards. So let's say a deck of cards. There are, in a normal deck of cards, there's 52 cards. And there are 4 suits. So you've got the hearts, the spades, the clubs, and the diamonds. And each one of those has 1, 2, well, I guess 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, ace. So there's all of these options. And the same for each one of them. I'm not going to write them all out. You want to have a particular card. So let's say that you want to have, let's look at how this was worded. Yes, there's a redundant one in there. So this is A or B or both. So let's say we want to have the 10 of diamonds. Or, well, not the 10 of diamonds, a 10 or a diamond. So there are 4 10s in here. You know, there's a 10 here, a 10 here, and a 10 here. So that's a 4 in 52 chance. And then the diamonds, there's 13 of those. So there's a 13 in 52 chance. So this would be the probability of a 10 or a diamond. Why did I write a 10 again? Diamond. So there's a 4/52nd chance of drawing a 10, and there is a 13/52nd chance. So I'm writing out this. And then instead of adding the probability of pulling the 10 of diamonds, you actually have to subtract that, because the 10 of diamonds is counted in here and in here. So because it's a 10 and a diamond. So you actually have to subtract one of them out because it's double counted in there. So that's why there's a subtraction on here of the chance of pulling the 10 in diamonds, which is just there's a 1 in 52 that you pull the 10 of diamonds. So you actually subtract that one off because you're double counting it in this first probability. So you have to be really careful with these. We're not going to do a whole lot with this kind of probability. You just have to know, you just have to be careful with the things that you're asking of your statistics, that you're not double counting things, that you're not, that you're specific about exactly what it is that does count. Does it matter if you do 1, then 2, then 3, or do you just need 1, 2, and 3 in some combination of 3 dice? Because those are different things. So you have to be careful when you define what it is that counts as your data. All right, so these probability density functions. So these are equations. Let's see if we can, we already looked at well, this is talking about the mean in terms of this probability density. And this is it for continuous and discrete. I actually wanted to get to the equation. All right, so we're going to assume most of the time that random data that we collect has a normal or a Gaussian. This is the bell curve symmetric distribution. And that's going to be our assumption for most data. That's when we plot the histogram and make sure that it actually looks sort of like a bell curve, because if it doesn't look like that, if it's skewed or if it's bimodal or if there's something different about it, then the stuff from here on out really starts to not apply, because we're assuming that you can describe the data with this. If you plotted this, this would be the bell curve, right? So this would be the actual normal distribution bell curve graph, if you want to call it that. Now it's got things in here like standard deviations and means, well, the standard deviation and mean. Here are a couple of different things that we're talking about for normal distribution. So this one on the left, this one has 3 different plots. They all have the same mean, so they're centered about 0. So their average value is 0, and then they spread out. So sigma is for population is the standard deviation. So how far from the mean does your data deviate? So the skinnier one here actually has the lowest deviation. And then the red one is spread out the most. It has the highest standard deviation. The other graph over here is showing different means also. So The lowest mean value for the population is 0 for the black line, and for the red line, looks like it's 10. This number down here is 10. So that's and it also has the same larger standard deviation. They're not the same width. So you need to know what standard deviation does to your data, or what it means to your data. It doesn't do anything to your data, what it means about your data, and then what the mean is talking about, which is like the average or the central tendency. In any of these cases, the red line, the green, or the black line on either of these graphs, if you were to integrate them, they always equal to 1. Now, they don't ever actually get all the way to 1, but if you integrate them, then you can force them to. But there's always, it never goes to 100% chance on either end, or a totally 0% chance on the other end. But the area under these curves is 1, and that goes back to the probability being normalized, so that there's a total of a 1 or a 100% chance that one of these data under the curve happens. Although never goes to 1, never goes to 100. Here's some Excel. So not everything has to be done in Python. Here are some Excel functions that can do these types of things. So you've got one that here's a normal distribution. So that's assuming that you have data that is symmetric, like the bell curve. You put in things like the average, the standard deviation, or the mean. I shouldn't say average, but the mean, standard deviation. These are population numbers, true or false, and it basically plots these things. It plots those for different means and standard deviations. And this is called the probability density function. So PDF, you'll see PDF. There's some Python commands that are PDF and PPF and a couple others, CDF, I think. And so that's PDF is talking about probability density function, which is basically this normal graph right here when we tell it to be normal. This one, so false and true is the different trigger on these two different options here. So false, you get the probability density function. The true flag returns the cumulative area under distribution. So what this is, do I have a picture? No. All right, so what this cumulative CDF, and that is another function in Python, in a library in Python. This one is basically the area under a curve up to a point. So words to try and figure out what they mean. Let's go here. So here's our normal distribution, and we have a point right here, we'll say. So the CDF will give us all of this area. So it just tells us how, basically, what's the percentage. It's going to be not going to be a percent, it's going to be a decimal, but what's the percentage of the area from the data point that we specify back to 0, I guess, or the left end of the plot. This one is just same normal distribution, except that we're solving for, we've assigned it to a variable p. We're solving for x. So now we have a value, an area probability, and we want to know what x is associated with that probability, or what data point is associated with that probability. Oh, there was that graph. This is, you'll have one of these, and if you remember looking at the exam 1 reference sheet or note card or whatever it's called on Moodle, there's one of these in here. This is basically so that you can do this stuff by hand. So this more or less is, and it shows you a picture, this is the area under the curve from 0, in this case this is the z distribution, so from 0 to z. And so you find a z value on your graph down here of 0.804 or 0.84, and that represents 29.95%, if you want to call it that, or 0.2995 decimals. If you're measuring from 0, this one is not measuring all the way from the end of the graph, it's measuring from the mean over. So obviously from the very left side of the graph to 0, that's 50. That would be 0.5. So this one doesn't actually go to 0.5 on the graph because I kind of assume you know that. So here's another example. I think we'll do this one in Python. I think the example is written in Python. So this is 3 different parts. So we've got 3 different means here, 0, 5, and 10, and standard deviations that go with those, 1, 2, and 4. And we're just going to plot the normal distribution. So this is like the very first set of graphs that had the different standard deviations. This is going to do that in Python. Part B, we have a given mean, 100, a given standard deviation, which is 37, and then we want to know the probabilities that 50, 75, and 140 or anything less than those will occur. So we'll have to draw a picture of what that's talking about. And then C, we have a given mean and standard deviation, and then what's the range of random variables that correspond to different probabilities. So kind of working problem B backwards. So let's go get, we don't need any data set for this. It's all coded into the Moodle file, in the Python file. So let's go get example 2. Let's copy all of that, put it into our Python code, make a new one. Let's go to the top of it and let's save it so it'll run. We'll just call this one example 2. All right, so problem 1, let's look at what problem 1 was telling us to do. It was saying we have 3 different means, 0, 5, and 10, and we have 3 different standard deviations for each. So 0, a mean of 0 has a standard deviation of 1. The mean of 5 has standard deviation of 2. The mean of 10 has standard deviation of 4. And we want to plot these normal distributions. So assuming that they're normal. So that's what these 2 lines are creating those, the mean, the A here is part A in our problem. So the A is just separating. There'll be some that are B for part B, some that are C for part C. So this is the mean for part A. There's the 3 different means. These are the standard deviations for part A. There's the 3 different standard deviations. So that's doing that. We go down here. Well, this is actually putting in the data for part B. So there's the mean, standard deviation, and those data points it was interested in. And then there's the data for part C. So this is just setting up the different lists with their different means and standard deviations for part A, B, and C. So that's what that's doing. We need to pyplot because it wanted us to do some plots. We need numpy because we need to do some mean and things like that. And then this one's new. This one is SciPy stats. I don't know. Let's see if I may have to get that one. I don't know if I have that one already installed or not. When we run it, we'll find out. All right. This is creating a figure, a 1x1. So it's just one graph on this figure. This is going to title it the axis and title. The axis lines, horizontal and vertical lines, are going to be K, which is black. So going to be black lines for the axis. And then here, this is one of the NumPy. It's kind of like creating a range. Well, it is creating a range that starts at -5 and goes to by 5 to 100. That's just so that we have. Remember, we just have this for our data, the mean and standard deviation. So we kind of have to have some range to plot over that standard deviation. We just are creating a range to do that. Here is this is the SciPy library, and we're going to create a normal distribution that has a mean of whatever was in the 0 index spot for our mean list, and has a standard deviation that corresponds to that in the 0 spot. So this would be the numbers. Nope. 0 and 1. So a mean of 0, standard deviation of 1. And then here we are plotting. So this is creating the actual plot. Here is the command to do PDF. This PDF is not talking about like PDF document, portable document format. This is talking about the PDF, the probability density function that we assume is going to have the normal distribution. It's going to be a black line, going to be a line weight of 2. These, I don't know that we've done these before, but this is a way to put Greek letters in. So the little $, slash, $, are kind of like quotation marks, but they're signifying that what's in there is going to be interpreted as some special character. So this one is going to be the special character mu, and this one is going to be the special character sigma. So this is going to be mu, and then we're going to put in the mean. And then, so it's a population mean. And this one's going to be the Greek letter sigma, and we're going to put in the standard deviation. So it's going to be the population standard deviation. And then until I uncomment this plot, it's not going to actually plot. So let's uncomment that legend, uncomment that plot. I think all the other plots are still commented out. No, that one's not. Let's turn these off for now so we don't get everything else going. I'm always going to print all that stuff out. That's fine. We just want the plot for now. Oh, wait, we actually do want these because these are, no, let's undo that. Actually, I'm actually going to re-comment this out because we're going to, we have 3 of these to do. Part A had 3 different things. So here's the other ones. So we're going to also plot a 1 or index position 1, which is the second one in our list, and index position 2, which is the third one in our list. These are the same kind of plots, except this one's going to be green, this one's going to be red, and they're going to have different axis labels depending on what their different means and standard deviations are. Then we're going to show the plot. All right, let's see if we run it. I don't know if I have the library for this. Let's see. No, I don't. No module named SciPy. So that was coming from right here. It looked for this, and I don't have it. So we got to go get it. Let's see if we can find SciPy. There it is. I'm going to install SciPy. Don't know how long it'll take. All right, there. Oh, it did something, but it's not done yet. So for yours to work, unless you've already installed SciPy, you'll also have to do this. All right, so it did it. Now let's try. Hey, there we go. All right. So here's our mean of 0, standard deviation of 1. So that was, oh, that one, I thought it was going to be black. Did it not say that that graph was going to be black? I guess it's going to be, oh no, it's blue. It's blue. All right. So it was just making these lines right here, this line and this line black. That was one was black. All right, and then the green line is the second one. It's tiny over here, but you can kind of see them. You would have to make this font bigger, or maybe on your computer screen they're larger than they are on mine, but that's tiny. That's the mu, so you can kind of see there's a mu there and a sigma there. That's the $ slash word mu $, generates that special character mu. And so that's the green one is average of 5 or mean of 5. So there's a 5 there, and it has a larger standard deviation than the blue one. It's got a standard deviation of 2. And then the red one is a mean of 10, so it's over here, and a much larger standard deviation of 4. So there's that little plot. All right, so it generated that relatively well. All right, and then, well, let's go through our code. So that gets us down to basically here. So here we are on part B. So part B wanted us to do, so that was part A. It plotted the corresponding corresponding normal distribution plots, assuming those means and standard deviations. Part B, we're given a mean of 100 and a standard deviation of 37, and we want to know what are the probabilities that 50, 75, and 140 or anything smaller than those will occur. So what that is referring to is basically this thing. So it was a I think it was the mean of 100 and a standard deviation of 37. So how the standard deviation works is more or less, you know, there's like 3 standard deviations here. So this one, if our standard deviation is 37, this number is 137. So hold on, 100 plus 37. The next one, add another 37. So this is 174. And plus 37, this one's 211. This one, and this one. This would be 100 minus 37, so 63. Whoops. Minus 37, 26. This one will actually go negative. Minus 37, negative 11 over here. So what was the first one? It was asking us what's the probability that the value of 50 or anything less will occur. So on our little graph that I drew, let's get rid of this stuff I already shaded in. 50 is like somewhere over here. So it wants to know basically what is that probability. So it's less than 50%. 50% would be if we shaded in from the center, the central tendency, the mean all the way left, that would be 50%. So it's less than that. So, you know, you basically, the percent of this area over 1 is the percent probability. So I don't know, it's going to be like 30-something percent, 40%. We'll find out. And so each one is asking that with different points. So 75 and 140. So 75, you know, is somewhere over here. So it's a larger percent that's going to happen. And then 140 is over here. So it's, you know, it's all of the 141 would be all of this area out of 100%. So let's go to Python. All right, so here we have basically said that we're going to create a normal distribution with the mean and standard of part B. We already defined those. Here we have the CDF. So we had PDF on that part A for probability density function. CDF is cumulative density function. So that is, it's accumulating all of the area from the left side up to whatever number we specify. So, you know, wherever it is. And then we have of different points, CDF of different points. So 0, XB0, we have to go back up to the top somewhere where we define that. Right there, XB0 is the 50. All right, and then it prints out a bunch of lines. The probability that the random variable XB0 is 50, or anything less than that value will occur is, we're going to print it as a string. We're going to round off PB1, which is this guy. NB is the normal distribution with the mean and standard deviation given in part B. And then PB1 is that mean and standard deviation, but we want the cumulative distribution function of XB0, which is 50. So it'll print out, and then it prints out the probability that the random variable value 50 or anything less than the value will occur is 0.0883. So 8.83%. I said it was going to be 30 something. So clearly my graph, well, my graph is not skewed, or not skewed is not the right word. It's not scaled correctly for that mean and standard deviation. That mean was 100 and the standard deviation was 37. So it should have been a different shape. And this would have been, it would have been more apparent that this little 50 number, oh, get off there. Oh, this 50 number was much further on the tail side because it's 8% or whatever it was. So basically it would do more, you know, it'd be skinnier. All right. And then it plugs in the next number. So the next one was 75 or anything less than that is 25%, 24.96%. And then the probability of 140 or anything less than that is 86%. So these are the percent chances or probabilities that this number or smaller will be drawn out of a hat if the hat is shaped like the mean of 100, standard deviation of 37. That's what that's telling you. And so this kind of thing is useful once you've generated the mean and standard deviation and assumed a normal distribution. then you can do things like this with future data. So you can go and say, all right, I've collected a whole bunch of data. I generated a mean and standard deviation of a normal distribution. And now I can say that, well, in the future, anytime that I get a value of 70 or less, I can expect that to occur, whatever percent of the time. And so that's useful for all sorts of either data collecting or process control or whatever, machine control systems. That is a useful thing. The last thing it asks us to do is the opposite of that. Or I don't know if it's opposite, but the parallel to that. We have a mean and standard deviation. There's that. What's the range of random variables that corresponds to different probabilities? So here we have 42 and 7 is what it said, I think. Oh, shoot. Made the screen go away. All right, I think the HDMI cable was very sensitive. All right, so a mean, I've already forgot. Was it 42? Something like that. Standard deviation of 7, and it had probabilities of 66. So we know that 66 is on the right-hand side. So 66% of the area. What is this number? Is basically what it wants to know. So we know it should be greater than 42. And then the next one it asks is, wrong slide, 75%. So then we'd find, 75%, maybe that's way over here, all of this area. And it wants to know what is that number. And the other one's like 99% or something, or 95%. So it's almost all the area and what number corresponds to that. So that's the last part here. Here's the XC1. We're doing a PPF. Here it is right here, percent point function. So it's not PDF like the probability density function. This is percent point function, PPF, corresponding to the 65, the 66, the 75, and the 95. So that's what these are corresponding to. And then it generates a whole list of outputs for there is and then here's the percent chance that the value of, and then that's just reading out the data here and chopping it off to 2 decimal places, or less will occur. So it's not the specific number, it's that number or smaller. And so you get, there is a 0.66 chance that the value of 44.89 or less will occur. So we hard-coded in the 0.66 and it generated the 44.89. So the number that's, right here was supposed to be 44.89, which, that seems reasonable. We know that our average is 42, and we know that it should be somewhat a little bit bigger than that. So 44.89 makes sense. And then these numbers should get gradually larger because we're doing a larger and larger percentage of the area under the curve. So 75% or 0.75 chance that 46.72 or less. And then to do 95% of the area under the curve, you'd be at a value of 53.51. So these, without some assistance, you can't calculate these. So you either need something like Python, Excel with its functions, or the one of these guys can even help with that. Where we're at. Okay, we're good. All right. So obviously these, example 1, 2, and 3, you should be able to download those and work through generating these different, it should just run that and it will generate all of these solutions for part A, B, and C. The student distribution, sometimes it's called the student T distribution. It is based on assuming a normal distribution. So you're assuming that the data is symmetric. The thing you don't know is you have probably a really small sample size. So you weren't able, for whatever reason, to collect lots of data to really be sure that it's a normal distribution, or you don't have enough data to calculate a very accurate standard deviation. You've got just a few data points. So it's kind of like you're guessing about this normal distribution. And so what it does, it's a little bit different function. As you get more and more data, this thing begins to look a lot like the normal distribution. But it's a way to deal with small samples, basically, which is what a lot of times you end up dealing with because for whatever reason, you're just not able to collect large sets of data. So it uses this idea of what's called degrees of freedom. So this V is going to be degrees of freedom, and it's just basically going to equal however many samples you did take minus 1. So that's this degrees of freedom value. And here is its probability density function. You are not going to have to deal. It's got the gamma function in here. Gamma function n minus 1 factorial. And so this is not something you're going to have to reproduce. You're always going to use the student t in association with a chart or Excel, or I guess even Python can do it, I assume. I haven't tried. But if you want to see, this is the actual plot that would create its distribution graph or line, if you want to call it that. In Excel, you remember you had the norm.dist. That was the ones that would assume that the data set you have is a normal distribution. There's a t.distribution. So this assumes that you've got a small sample size, and it bases the solutions on this equation versus on the normal distribution equation. And these look very similar to the ones that were normal.dist. And they do the same kind of things. There's a probability density function. There's a cumulative distribution function. Well, that's just showing you the integral form of it. There is calculating a x value given a certain probability. This is 2t, so basically the difference here, and they show these graphs. So the 2t is two-tailed. Sometimes the number you want to put in, you want to specify that you don't want, you're basically trying to set up a range of values or anything outside of a range. And so there's two tails, or there's just a single-tailed version where you just want to know up to that point or smaller. And so the difference in here is in this little .2t in the Excel function. There's also a chart for it, a single-tailed chart. And then we have an example for that. So let's grab example 3, and then I think we'll have plenty to think about for a while. Moodle, where'd it go? There it is. All right, example 3. Let's copy all of that. There we go. Go over here, make us a new one, paste it, save it. Save. Let's make this one number 3. And we'll go through what it does. All right. I guess we should look at the problem we're solving. All right. So for the student distribution, so this is a distribution where we're plotting the distribution for the degrees of freedom of 2, 7, 16, and 30. So this would be a sample size of 3, sample size of 8, sample size of 17, sample size of 31. So as we have larger and larger samples, this plot will approach looking like the normal distribution plot. In fact, that's what part B says, is to basically plot on top of these 3 what a normal distribution would look like. So here are our different degrees of freedom. New 2, 7, 16, and 30. Those are the sample size minus 1. We need pyplot because we're going to plot something. We need numpy to calculate some of the mean, we'll have to see what we're using numpy for. And we need scipy because we wanted to use the density function stuff. We create a single plot with some black axis lines and some titles. We create a range so that we have some space to work in. So these are the .t is the t distribution, or the student t distribution. SP is scipy, and we've created 4 different ones, one for each of the different degrees of freedom. And then we're creating the plots. So we created a blue, a green, a red, and a yellow plot. They're all line plots. That's a little dash. They all have the same line weight. Here's where we're creating the little symbol new that looks like the V. And we're going to plot those different, well, right here. Where do we put those? Well, new 0, 1, 2, and 3. So whatever their values were. So this is just putting the, well, here's putting the actual graph probability density function, so the shape of the curve, the bell curve, for the different t distributions. Here, this part is creating the normal distribution on that same graph. We're going to make it black, same line width, label it as the normal distribution. We're going to put the legend in the best spot available. All right, so this should run just as is, so it shouldn't do anything to it except make it bigger. All right, so we could do with larger, thicker line weights, but blue, and you can't barely see, but blue would be the t distribution that you could use if you took 3 samples. So you took 3 samples of this random data and you want to extrapolate out the entire probability for a data set based on those 3 samples, and it would look like this blue line. And then you take more samples. So you take, I think the next number is 8. So the green one is 8. So this black line at the very top is the actual normal distribution. So that's the one you've taken many, many samples, and you have the normal distribution curve for the black line here. And then you can see as you take more and more samples, student T begins to approximate the shape of that black line. So it is a way to use small data sets. Obviously, the smaller the data set, the more errors or more uncertainty you'll have in the resulting probabilities, but it is a way to use small data sets that approach, as you increase the sample size, approach what the normal distribution would tell you. All right, so this one's actually really easy. Most of this is setting up the plot. Only here's creating the actual distribution, the t distributions right here. And there's the plots. Maybe they're a little easier to see. The only difference here is the one on the right has the normal distribution as a black line on it.